Swayam Prabha. Digital India. Educated India.
Okay, so welcome to Introduction to Civil Engineering, part of the lecture on structural modeling. I am Dr. Pratapa. Some of you might know me. I am a faculty in structural engineering here at IIT Madras in the Department of Civil Engineering. So today we will be looking at some part of structural engineering and mechanics, which is called structural modeling. So in this lecture what we will see is, we will first understand, we will look at some examples of modeling and simulation and what modeling and simulation actually means and what does it mean in the context of structural engineering and mechanics. We look at a very simple example in terms of what you actually know from before you came to IIT, and then see how that transforms into computer models and how does it help to solve huge problems, complex problems in civil engineering and structural engineering. And then we will also see after that how this structural modeling can enable to venture beyond the horizons which we already know. That is, maybe discover new types of structures, new types of materials, model new kinds of structures which you haven't envisioned before and all that. And then we will see how it's kind of changing the phase of innovation and technology and all that in the end. Okay, so let's start. So here I have an animation or simulation of a computational model. You can see that it's a model for blast loading in a building. So what's exactly happening, if you notice, is at the bottom there is a blast and a column at one of the corners. This column starts failing, and that leads to a progressive collapse towards upwards. Each slab and each of the structural elements in the slab keep collapsing, and then there is a collapse of the entire section of the building. So these kind of things can be studied well in advance, even before such things happen. You can try to predict how a building might fail if there is a blast load, and then maybe try to strengthen the building for different cases and come up with innovative designs. And this is another simulation of a building subjected to earthquake loads. So what is an earthquake load? An earthquake is where the ground shakes. So in this case we are looking at a ground shaking happening in a lateral horizontal direction. And then you have a simulation of a structure which is on the ground. So you can study how the forces or deflections of the members of the structure are varying as the ground is shaking. And this will give you a sense of what is the maximum stresses or forces that my structure can take. Is it good enough? Will it be safe? And if it is not, can I maybe resize my structures? Like for example, can I make my beams and members larger in size so that they will be more stronger, right? And this is another example. We will just look at these three examples and then we will go into the course. So this is another example I thought is interesting. So this is a suspension bridge. So in a suspension bridge, what you have is, you have a deck, right, and it is suspended from cables at the top. And suspension bridges are very important because their dynamic characteristics are very important, because when you have a bridge, it's subjected to dynamic loads, vehicle loads, wind loads, earthquake loads and so on. So why are dynamic loads difficult to understand, and why is it important to understand structures in the context of dynamic loads? So think about a simple pendulum. Let's start with the simplest object you know, a simple pendulum oscillating. A pendulum oscillating has a natural frequency or a time period. What is that? It is the time taken for the pendulum to complete one oscillation. And if you see, I have shown here three pendulums, one in blue color, other in a golden color and a black color. And what is difference between them? The length of the pendulum is different. That is, their geometry is different. So if the geometry of a structure, in this case the simple pendulum, is different, it can have a different frequency of oscillation. You can see the blue one is oscillating much faster than the black one, right? Similarly, when you look at a structure, depending on the size of the structure, the material you used in the structure and how the structural members are connected, you can have different modes of oscillation. In the bottom figure, I showed 4 different modes of oscillation. In a simple pendulum case, you just have one mode of oscillation, so there is just 1 degree of freedom is what we call it. But in a structure, there are different kinds of oscillations that are possible. For example, you can see the first figure is more like a sinusoidal curve, right? But the second one is more or sort of a lateral torsional oscillation. So different such oscillations are possible, and each oscillation has its own frequency depending on the geometry of the structure. So in summary, it's just all about how this geometry and the material property is going to affect your frequencies, and how these frequencies are related to the dynamic forces acting on the system. If you can understand that, you can design the structure better for the dynamic loads. So now let's get into what is modeling and simulation. So what are models? This is quite a general concept as I wrote here. Models are used to understand, explain or predict something. They could be theoretical models, mathematical models, numerical models, computational models, statistical, phenomenological and so on. We will see some of these in the next few slides, what they actually mean and how they are different. And then what is simulation? Simulation is recreating a system or a process or a phenomena. For example, here I have an animation, right? So this is about computer simulation of a car crash. So if I want to understand car crash, I don't necessarily have to crash the car thousands of times in different directions. Maybe I run a few thousand simulations and then finally test one or two of the critical ones, right? And when I want to do that, what I need to understand is I want to understand a mathematical or a theoretical model for the structural chassis of the car. And then do some computer simulation, solve this problem on a computer and then I can visualize what's happening, right? So these are some examples of modeling and simulation. So the first one is weather forecast. So let's say you want to predict the path of a hurricane or when the cyclones would come, which states the cyclone would cross and so on. This is very important for irrigation purposes and many other water resources problems, right? So this is typically done based on previous data and also you could maybe use atmospheric physics. So it's a combination of physics and data problem. Financial engineering is related to stock markets. So you have a stock market data based on many years, the trend of the stock market, and then you want to decide whether you want to buy a stock or sell a stock depending on how you think or how you predict the stock market is going to behave in the future. And for that you need a model for it. So this is typically done using statistical modeling. And then there are also other models, for example, atomic molecular interactions have to be modeled if you want to design drugs for some diseases, right? I want to study how the molecules are going to interact, form the bonds or maybe break some bonds to create new drugs, maybe for cancer or some other diseases, right? So such research can be done if you model atomic interactions using maybe some experiments as well as some physics based laws. And another example on thermal analysis. So this might sound a little interesting because here you are looking at a computer motherboard. So the animation or the figure here, the colored figure here shows a computer motherboard and what we are trying to do is cool down a processor. It gets pretty hot in the processor on the computer motherboard and if it crosses a critical temperature, the parts can fail even structurally. If it structurally fails, your circuits are now no longer connected and it cannot function, right? So you want to keep the temperature of the processor below a minimum level and maybe for that you want to design a fan. So now how do I decide what should be the shape or design of the fan, what should be the speed and all that, right? For that what I want to do is I want to study how the wind passes through this processor and how does it dissipate the heat. For that you want to do thermal analysis. So that is a modeling and simulation that can be useful in the context of thermal analysis. And what about fluid mechanics? I show here a aircraft. So in aircrafts you have wind flowing on the surface of the body of the aircraft and if you can model the wind flow on these structures, you can potentially reduce the drag on the system. So if you are moving your hand in the wind, you can see that you have a resistance, right? So if I can model that wind on this surface, maybe I can model the shape of my surface in an efficient way so that drag will be lesser. If you move it like this versus like this, there is a difference, right? So that is what you are trying to understand. So that is related to fluid mechanics because air is a fluid. And then finally we look at structural analysis, which is the main theme of this lecture, right? We look at the overall context of modeling and simulation in the context of structural analysis. So before we go into the actual talk, let's motivate ourselves why computers are important. I am sure you know why computers are important for various reasons, but in the context of modeling and simulation, why are they important? Let's start with the basic problem, one of the basic problem. So can you solve Ax equal to b, right? So what do you need to solve Ax equal to b, an algebraic equation? You need the input a and b, and then if a is a real number and b is another real number, you should be able to tell me what x is. For example, if 2x equal to 3, x is just 3 by 2, right? Now what if I say a and b are not just single numbers but they are matrices, right? So if a is a 2 by 2 matrix and b is another 2 by 2 matrix such as the one shown in this example, can you find me a vector of size 2 by 1 from this given input? Which is quite trivial. You just have to invert this matrix, which can be trivially inverted for a 2 by 2 matrix as shown here, and then multiply with the right side vector, you get your unknowns x1 and x2. But then if I ask you, can you solve this matrix system with an n by n matrix and an n by 1 vector on the right hand side? So you are basically, I am asking you to find x1, x2, xn where n could be maybe 1000. I am asking you to solve 1000 equations at the same time. Can you do that manually? No, right? So why don't we use computers for that? So let me put this into a bigger context. So what are computer models made of, right? So I have this numerical problem in terms of a huge matrix and a set of unknowns x1, x2, x3, xn, and then given b1, b2, bn, right? So let me give you a physical context of what this means. At the right bottom corner on the screen, you are looking at a beam which is undergoing some sort of animation. I'll explain what is happening. So imagine this b1, b2, b3, bn, each element in that vector corresponds to a vertically downward force at each point on the beam along the length of the beam. So let's say I am applying a b1 here, b2 here, b3 here, and so on bn, right? Now correspondingly, if I am pressing a vertical force on the beam, there should be a displacement at those corresponding points. Now I will denote x1, x2, x3, xn as a corresponding displacements at all those forces. So now if I solve this matrix problem A times x equal to b for a given set of forces on the beams, I can find the given set of I can find the corresponding displacements on the beam. So that is a structural analysis problem. Now once I establish the context of this problem, I have this numerical problem which I have to solve. I have a matrix, I have a force set, and I want to find the displacement on the structure. How do I solve this matrix problem? Right? It's a linear algebra problem. You typically have algorithms or solution procedures for standard problems in terms of the properties of the matrix A. So for example, you might have heard about Gauss elimination method, right? On how to solve a matrix with a lot of unknowns and so on, right? So you can use such an algorithm, or you can use different algorithms such as the ones shown here, and that should be able to solve the problem. So that is all theoretical. You have a mathematical framework or how to solve Ax equal to b. Now, how do I use a computer to solve a problem? Because even if I have an algorithm, if I have to solve a 1000 by 1000 problem, I cannot do it manually, right? So I need to tell a computer of how to understand this mathematical algorithm and solve it. For that, you need to use what are called programming languages like C or Python or Fortran or MATLAB or whatever you are comfortable with, and then translate this algorithm which is shown in this green box into a code or a software. So once I have my software, all I need to do is give the inputs to the software, which is all the elements of the matrix A and all the elements of matrix B, and then this software using this algorithm should be able to solve for all the vector xi, right? So once I do that, I can visualize my results using graphics, which is shown in the last part. So what is happening here is actually I started with a set of forces b1, b2, bn, and I kept increasing the magnitude of the forces. I kept making the forces larger and larger, and at each point I am trying to find my displacement x1, x2, xn. So as you can see, as the forces are increasing, the displacement is also increasing, right? For each of those I am solving that matrix problem. So now let's see how one could develop a theoretical or a numerical model for a typical structural engineering problem, right? So you are all familiar with Hooke's law, right? If you have a spring and if I apply a force on it, the displacement of the spring is or the elongation of the spring is proportional to the applied force, and this is the standard basic Hooke's law, and it is given by this expression kx equal to f. So in this case, f is the input variable force on the spring and x is the corresponding elongation. So this is also shown in a plot here. So the x-axis corresponds to the displacement of the spring, y-axis corresponds to the force, and let's say you take a real spring and start applying forces, maybe 10 newtons, 20 newtons, 30 newtons and so on. For each force you have a displacement. So once I have that, I will mark the corresponding displacement and I will make a plot as shown here. Once I join all the lines, firstly I will notice that they are falling on a line, and once I join the dots, I get a slope of the line, and that slope is nothing but the stiffness of the spring given by k. Similar analogy can also be applied for a steel rod. Steel rod is also a spring, except that the stiffness of it is much higher than a normal spring you see, right? So again you have a Hooke's law for a steel rod, and why is this useful? Now once I have a model, so let's call this the theoretical or the mathematical model for a spring or a rod derived based on experiment. Once I have this model, next time you give me a force applied on the spring or the rod, I do not have to go back and do my experiment, right? The model is now able to predict the displacement that can occur in the rod. So that is the idea behind developing a theoretical model. And this is very simple and it's kind of obvious if you can think about it, right? But now let's go into a slightly complex problem. So let's say I have this water tank structure shown here, right? And then I am saying I want a model for this structure, because in the end all I am interested in is I want to apply forces on my structure at different points. Let's say F1, F2, F3 are various forces applied at different points on my structure, right? And for those corresponding forces, I want to find the corresponding displacements, because those forces will cause some displacements or distortion of the structure. That is what I want to do. What do I do based on my previous experience? I have to do an experiment. So if I can do an experiment with forces and displacement and make a plot and maybe potentially find this K full, the stiffness of the structure, then I am good, right? But how easy is it to perform experiments on structures like this, or maybe more complicated structures, which we will see eventually, right? It's not quite feasible. At this point, we use the math and develop what is called numerical models. Since I know how to deal with a single rod, I can approximate this entire structure as a combination or a network of many bars which are subjected to forces. So each bar here is connected to every other bar, and it kind of approximates this real structure. So when you are approximating, you know you are dealing with a model. Now this is a numerical model, right? And since I know for each bar, I can write K1 x1 equal to F1, because each bar still obeys the theoretical Hooke's law which we saw in the previous slide. And for the entire structure, all I have to do is combine all the equations from the bars and develop this huge matrix, right? So this huge matrix times displacements at each of the rods and the forces on each of the rods is what dictates the structural behavior of my complicated structure. So this what represents a numerical model for this problem. And once you solve this numerical problem on a computer, because it is so huge and you cannot solve it manually, that becomes a computational model. So you take a real structure, you convert it into a numerical model, and then you solve the problem. That is, maybe you press some buttons here, but what is actually happening once you press the buttons is that the code is running and is trying to solve the matrix problem, and is giving you the displacements or forces or whatever you asked it for. And then you can visualize the results and see and make sense whether your structure is safe, or are you okay with it, do you want to change it, and so on, right? So let's put it in the overall context of what you might have seen in the previous two classes on structural engineering. Maybe you heard about analysis and design and so on, right? So what is happening? When somebody wants to build a structure or a bridge or something, they start with an idea. Yes, I want to build a bridge here, or I want to build a building in this location, and this location is characterized by such and such atmospheric forces or temperature and so on. And this is a material requirement, these are available in this location, these are not, and so on, right? Based on all that, you start with an initial design or a preliminary design for your structure, right? And once you have your design, based on what we just saw, you cannot do a full scale experiment for it. In some very rare cases, although that is possible, but in general, it's not possible. So you construct a computational model for the initial design, and this computational model is informed from theory, experiment, as well as mathematics, right? So once you have your computational model, you run it through a computer and perform the analysis and see whether the structure is safe and acceptable. Whether that design you came up initially, is it safe and acceptable? Can it take all the forces without failing? Will the structure stand or will it fall? If it is safe and acceptable, you end your design and you're good to go with your initial design. If not, you go back, maybe change the layout of your members, or you change the sizes of the members to make it more strong or less stronger or whatever you want, and then go back and update your computational model again, because now you change your structure, and then perform the analysis. And this loop keeps going on until you are satisfied with it. These are what are called design iterations. Typically, if you are performing any structural analysis or building a new structure, many hundreds of such designs are possible, depending on the complexity of the structure. Now imagine if you don't have this computational modeling capability or structural modeling capability, you would have to perform an experiment for each structure you come up. Every time you change and you think this is not good enough for me, you have to perform an experiment, because you don't know the stiffness or the property of the structure, right? So this analysis actually is cutting down the time on your design iterations and helping you design the structures more efficiently. So now let's look at some applications on how this structural modeling has helped in designing some of the most complicated and wonderful structures on this planet, right? So this, I'm sure you might have seen in other lectures in this course. Burj Khalifa, one of the is the tallest building on the planet, right? And there are some interesting aspects to it from the context of structural modeling and simulation. So firstly, when I say you have a very tall building, extremely tall building, what is that comes to your mind? Imagine you are on the top floor of the building, high wind loads, right? There's going to be very high wind loads. So how is this building different from any of the other buildings? Because you are at such high level, maybe you have a stream of jet winds coming onto your building, and that might affect some structural dynamic behavior which we have discussed in the beginning, right? So what typically happens is, if you look at this blue part of the animation, I am showing you a cylindrical structure which is put in a fluid motion. So the fluid, let it be wind or water, it's moving on the cylinder, and once the velocity of the fluid crosses a particular point, you will see what is called vortex shedding, which is happening here. So there are some kind of features in the fluid that keeps moving out away from the structure, and if it is happening at some frequency that can resonate with the structure and make your structure oscillate, and that can be very bad for your structure. It can even lead to collapse of the structure. So you do not want your structure to be a cylinder and standing so tall and your wind is so bad that you have vortex induced vibrations, what they are called. So in order to overcome that, the designers have come up with this interesting design where they have cylinders staggered as you go up. If you see the structure, there is some sense of spiral action going on here. So the cylinder height is here, and here it is higher than that, here it is higher than that, and so on. So this staggered pattern disrupts this kind of periodic shedding that is happening on the structure, and it will prevent vortex induced vibrations. And if you see the final wind simulation of the building, you can see there is no such periodic shedding happening. It's all dissipated here, and that is how you know this building is not going to fail under such wind induced loads. And all this is possible if you could just simulate it, right? It doesn't cost much. But imagine you would have to make a real experiment of such a large scale structure, it's not possible. There are some extreme cases, like I said before, maybe you can make a scaled up model of the structure and then test it in wind tunnels, but even that is pretty expensive. But compared to making a computational model and studying which wind loads are the most critical is much easier, right? And this is another example where you have an earthquake load in the building, so it's oscillating in different modes. So you want to study again which dynamic modes are critical for the building and so on. So now if you see those buildings, and if you count the number of rods we said we will describe the structure with, you can imagine your matrix size could be running into thousands, right? In some of the cases it will be of the size million by million or 100,000 by 100,000. It will be in the orders of millions in many of the structures when you have very small rods approximating such a huge structure. So can your computers actually solve that problem of a million by million matrix times some vector is given forces? A simple standard computer cannot necessarily solve very huge problems. In such cases you have to deal with what are called supercomputers. So for that, what you need to understand is this high performance and parallel computing, and I thought it is very important that you know about this, at least a little bit background on this, because in today's world most of the computers, even the personal computers you are using parallel computing. Parallel computing need not necessarily mean you have 10 computers in front of you. All you are doing is you have many cores, and whatever job you are giving out, so let's say I have to make some calculation. I don't want to make the calculation one after another. I want to do them all parallelly. So let's see how that works. So let's say I am interested in a matrix times a vector. So I want to calculate this matrix times vector. So how do I typically calculate? I calculate B1 as product of this row times this vector, right? So A11 x1, A12 x2 and so on, A1n xn. Only after that I can go to B2 and do this row times this and so on. So if I were to write a MATLAB code for this, you have it here. So for I equal to 1 to n, that is for each B1 or Bi, calculate the product of the row elements of the matrix Aij times the corresponding elements of the vector xj. And the way this thing works is, first it will calculate B1, then it will calculate B2 and so on. So what we suggest to do is, you run it on multiple computers, the first loop. So what I want to do is, I want to calculate B1, B2, B3, Bn all simultaneously. And just to get an intuitive understanding of what's happening here, I have a couple of figures taken from the Lawrence Livermore website. So in the first figure, you are looking at plowing a field. You have one tractor or one machine, you want to plow a field versus 100 tractors going at the same time. You can finish the whole field in the time taken by one tractor to traverse the field, right? Another case, you are constructing a building, one worker versus 100 workers working on it at the same time. So that's the idea. So now what we want to do is, I will calculate my B1 in one computer or one node or one CPU, and B2 in another CPU, B3 in another CPU and so on. But what we need in extra to what we already have with our standard computers is, we need a network which connects all these computers to tell me that these B1, B2, B3 belong to the same problem. And that is called a computer cluster. And there are many thousands of computers that can be connected, and very huge problems can be solved on them parallelly. And let's look at an exotic example of structural modeling. I thought this is interesting because it would give you a sense of how can I come up with a structural model for a structure which I haven't seen before. For example, I haven't seen this structure before. This is a folded structure made out of a flat sheet of paper, and it turns out it has some very interesting properties. So you see, there is a flat sheet of paper, and somehow I folded along it some corrugations, and you end up with this structure, right? and each part of this cell is again shown here in detail, just for you to get a understanding of how it looks. And let's say I want to model it structurally. So before I go into structural model, I want to show, I have a paper model here, you can come and see it after the class. So it has an interesting behavior. If I pull it out, it extends in both the directions. Why is this interesting? If you take a rubber sheet and pull it out, it contracts in the other direction. But in this case, if I pull it out in one direction, it's extending in the other direction, right? So this is called a Mura origami sheet. Origami is the art of folding paper. So now let's say I want to do a structural model for this. So I take my unit cell, I understand its geometry in terms of something shown here, but now structurally I want to model it. What do? I go back to my idea of replacing the structure with bars, right? And bars are nothing but springs. So I have a quadrilateral panel here. Firstly, I replace my quadrilateral panel with a set of 4 bars. Then I understand that the opposite corners of the quadrilateral panel cannot be independent. They cannot just go out as they want because it's just a plate, right? So they have to be quite rigid. That means I have to put another bar connecting the diagonal. That is a more realistic representation of this panel, right? So that's how I come up with a model and I put some springs on it to give a structural behavior. And after I do that, I model it on the computer, right? I simulate it on the computer. And you can see it can give the same behavior as I have shown you. As you pull it out in one direction, the other direction expands. And if you contract in one direction, the other direction contracts, right? So this is how structural modeling can help you understand structures which you didn't know how they would behave, for example. And there are also other systems such as atomic systems, such as one shown here. So this is a combination of graphene and carbon nanotubes. These days you might be hearing a lot of these buzzwords, carbon nanotubes, graphene and so on. They have interesting properties, electronic properties and so on, right? But even structural engineering has a role to play over there. Why is that? In the end, nobody wants things to fail structurally. If I am making an electronic circuit or a PCB or whatever, I don't want it to break. I want it to be strong enough for whatever stresses even if that is undergoing. Even the smallest things are subjected to forces. I don't want them to break, right? So in this case, researchers have found that if you combine carbon nanotubes, which are shown as pillars here, so these are carbon atoms, and then if you combine the graphene sheets, they have a better structural property than both of them working independently. And this has a lot of applications in electronics. And as structural engineers, I see them as columns and slabs and beams, and it's the same concept, right? In fact, the researchers who found this idea were civil engineers from Rice University. So this is another interesting application of modeling. In the previous flowchart where we discussed design iterations, I said once you are not happy with your design, you go back, change your member sizes and analyze it again. But doesn't it seem a little bit inefficient that I have to tell the structure what to change, what to increase, what to reduce and so on, right? It would be nice if I have some sort of model, maybe an optimization model, which tells the structure, no, now you want to remove the material there or maybe increase the material here to make it more efficient. So that is what is happening here. So I start with a cuboidal domain shown in blue color initially, and then I applied a load at the top, and then I gave it a modeling algorithm which says remove the material which is all inefficient, which is not taking load efficiently, and that is going to give you the beam structure which uses the least amount of material. And if you can use such algorithms to design futuristic buildings such as the one shown here, you can get these kind of bracings which are similar to what you might have seen in standard buildings but are also slightly different. And these are supposed to be at least theoretically optimal and more efficient in terms of structural efficiency. And if we have time, we can go over in detail on what kind of cantilever structures you can obtain using this algorithm. I think you might have seen the cantilever structures in your previous lectures. So cantilever is you have support on one end and I apply a load somewhere else, and in between that I want to create a structure which can take this load to the support, right? So that is explained in this figure here. And these are some examples of cantilever structures where you have the support on one end and you have a huge structure in between. So let's see how they compare to what this optimization algorithm would give. So the optimization has told me that if this length is small enough, I just need a V-type brace, and as you increase the thing, you need more and more braces to transfer this load to the support, right? But one thing is common between what is existing and what are these. Braces are common, but the way the braces look and the amount of bracing that has to go at one end versus the other end, that is changing, right? So of course there is hope that you can make structures more efficient maybe you can use 50% of the material that was used in this to get the same structure and be more efficient, right? So all this sounds good and it looks interesting, but can we actually build it, right? That's probably the question you have in mind. So here is an example of concrete structure. This column is made out of concrete, and typically you might not have seen concrete in some random forms. But even if you have to build a concrete in some weird shell shape and so on, you have to take a lot of effort to make the form work for the concrete and so on. In this case, they have used 3D printed form work to make this complex 3D structure. So what I would like to highlight here is, it's not impossible to make structures which were not possible before. There are always advances happening in the field to build structures using innovative techniques, and what you thought might not be possible might be a reality tomorrow, right? And another surprising thing is, you even have 3D printed metal lattice structures, and these are right now actually being used in the industry. So industry is actually 3D printing metal lattices to be used in automotives or manufacturing and so on. So that already has become practical. Can anybody guess what this is? So does it look something like a part of an Eiffel Tower? Right? Maybe it looks like this truss structure, right? But if you notice this length scale I showed here, it is telling you that the length measurement from here to here is 10 micrometers. What does that mean? The entire width of the slide is about the thickness of your hair strand. So somebody actually sat down and used some advanced manufacturing techniques, maybe such as 3D printing, to build a structure within the thickness of your hair strand. And that structure is inspired by the big scale structures like Eiffel Tower. And why is this important? How does this make sense, or who cares about this, right? So if you think about it, when I was talking about the optimization algorithm, I was talking about removing the material which is not taking the load and making the structure more efficient. If I am using less material, I am causing less environmental impact in some sense. So that is one of the motivations you want to design your structures in a more efficient way, right? So if you are removing material which is not being used, you are making the structure light in weight and also having the same strength. So you are making your structures lightweight and high strength. So many of the structures you see around, maybe they have too much weight just because we do not have any other way to manufacture them. So you don't want to do that, right? So these are called mechanical metamaterials. They are made in some exotic ways and they have some exotic properties which you might have thought are not possible. So another example on mechanical metamaterials. So what are metamaterials? Just a definition here. These are artificial materials that can exhibit exotic engineering properties. What is exotic? Something fancy, something you thought it doesn't make sense to me. Maybe something like that. So let's look at this example. Invisibility clock. Maybe most of you know about Harry Potter's invisibility clock, right? So it's a garment. When you enclose it around an object, you will not be able to see the object. Does it physically make sense? Is it just pseudoscience or science fiction or something, or does it make sense physically? It can be explained physically, but the practicality is a different question. So let me try to explain what is actually happening when we talk about invisibility clocks. So on one end, the light waves are coming in and there is an obstruction and somebody is viewing the light waves from here, right? If there is an obstruction, I should not be able to see what is there behind it. That is a reality. Now if I can make some kind of metamaterial around this, which will behave in such a way that it will take these waves, it will manipulate them in such a way and send out the same waves as they are coming in, such as the one shown on the right side. If I can do that, if somebody is sitting here, they will exactly see these light waves as they are here, which means they will not see what is there here, the black dot they will not be able to see. That is the idea of invisibility clock and metamaterials associated with it. So practically we still do not have it yet, but I take inspiration from this towards what are called elastic or acoustic metamaterials. Instead of light waves, let's say you have sound waves or maybe structural vibrations. I can use the same idea to create some sort of metamaterial around some structure I want to protect and make sure maybe these waves do not touch my structure and just go away, right? So that is explained in this simulation here. So let's say I have some metamaterial shown in some sort of this lattice shown here, and then you have some vibrations on one structure, and I don't want these vibrations to go to the rest of the structure. Now if I can design this geometry of this structure using some optimization in such a way that these vibrations cannot pass through this, that is they will be repelled or absorbed by this lattice, then I can protect this part of the structure. So you can isolate the vibrations. So another example is wave guiding. So I have this lattice, and then you can maybe distort the lattice in some way to make the waves propagate in some particular direction you want, right? So theoretically this is all possible. There are challenges, there are limitations, but the good thing is now theoretically it's not, it doesn't seem nonsensical. So let's say I have a sensitive structure, maybe a nuclear reactor, and I can put such a lattice grid below the ground, and then if I can maybe play around with my lattice and design my geometry of the lattice, you can potentially control the vibrations, maybe earthquake vibrations coming to the structure, go around the nuclear structure and make it safe, right? So the modeling and simulation, the importance of that context here is you still do not have these systems, you don't have any experiments, but the theory and the models that have been developed fundamentally can be extended to more complex ideas which can result in futuristic structures and materials. That is what I want you to take away from this. And now let's summarize. So I'll just go over briefly on what the major topics which we have touched upon. So the first thing is models are intended to depict reality. Models are not reality. We want them to depict the reality as best as we can using experiments or other insights. And theoretical and mathematical models are typically derived based on experimental observations in most of the cases, but also there are cases where you can derive from first principles or fundamental laws. For example, maybe Newton's law of gravitation or maybe quantum mechanics can be used to understand atomic interactions using fundamental laws, not necessarily entirely based on experiments. And computational models are obtained by solving theoretical models on computers, which we have seen, and we have seen the importance of parallel computing in solving large scale structures. And structural modeling is useful to calculate properties of structures which are very difficult to obtain from experiments, and this is what we have highlighted in this lecture. And we also noted that it reduces the time taken for each design iterations. It makes the designing process of the structures more efficient. And structural computational modeling is useful for analysis as well as design. And this is a novel concept relatively in the sense that the optimization frameworks that can also design the structures are not very rigorously or widely used in the industry yet. So there is a transitioning phase that is coming in where now you can design and analysis, do everything with modeling. At least that can give you an insight on what the best designs can be, and then of course you can have the human factor in to make it more practical. Finally, latest advances in manufacturing and construction technologies make structural modeling all the more relevant and critical for rapid technological progress. Finally, I would like to conclude with this slide, and I believe that human creativity plus computers make advanced technological innovations feasible. Thank you.